Hello, higher algebra students, here with lesson 5 of Unit 5, which covers linear programming. We aren't going to really get into the meat of linear programming. Just a little background on it in general is that it can be complex in the real world, and it's really a method to achieve the best outcome in a mathematical model. So it's like maximum profit or lowest cost, and it's represented by these linear relationships. And so you can see, obviously, to optimize here, as it notes, it does involve graphing some inequalities and things like that. And so it's a little bit of review of what we've done on the algebra side, but just a different real world application. And so when we look at it, you can see here's an example where we have this line x equals 5, and this is the same one over and over, but x equals 5, that we're to the left of that line. We're clearly to the right of the y-axis. We're above the x-axis here. And then we're below this line here, this 2x plus 5y equals 16, which then we've got these four boundaries, and those boundaries could be costs and profits and things like that, um, that we ultimately find this space here that would be kind of the optimized space. And that optimized space, again, obviously this isn't enough context here for that, but that optimized space would be like how a company would function to ensure that they aren't using more inventory than they have in terms of parts or something to make an iPhone, for instance. But then that they're also maximizing what they can sell it for, and maximize the profits in the end. And so just some other examples here. Again, looking most efficient, least costly, most profitable, best. And here's a bunch of kind of individual scenarios. So shortest route to visit a bunch of cities, optimal route to go to a few, run a few errands and go to a friend's house, materials to use for building a house, like cost and quality of those, even foods to eat for an Olympic athlete and considering cost, training versus fatigue, optimal transportation systems, so busing routes or light rail routes, bike paths, things like that. Um, that are optimal for getting around a city like Minneapolis. Um, Optimal bike car design, lowest weight, aerodynamics, and so forth. All of these can be, I don't want to say reduced to algebraic models, but really kind of determined by going through these algebraic models. Farming, things like cost of seed, care, maintenance, profit, resilience, nutrition, cost, nutrients, calories, and the like. So again, all areas that could then be kind of converted over to these algebraic models. And so this is a pretty wordy look at it, but here you have an idea of a toy manufacturer. And this toy manufacturer here um, wants to maximize their profits. And so they have a certain amount of, in this case, wheels. They have a restraint, a limited supply of wheels. Okay. And they're making toy tractors that sell for $6. They're making toy cars that sell for $5. That's another constraint. And so this is very simplified here, but then if Z represents profit, and you get $6 for every tractor, so X represents tractors or number of tractors, and $5 for every car, and again, capital Y, that represents the number of cars. Um, and then you have other things like demand. How many people want to buy tractors versus how many people want to buy cars. And so this model, while more complex than is shown here, takes into account all these all these equations really to determine what the best model is for this toy company in selling their cars and tractors. So if we take the sort of real world context and pull that back and just the algebra side, okay, this would be an example here. So as we look at, we've got three equations here, and again, x being less than or equal to 7 might be, something like how many, maybe there's 7 or less options for a certain, I don't know, recipe or something like that. And so what we're going to do is we're going to go to x is less than or equal to 7. So again, x being 7 would be right here, and it's less than or equal to, so it's a solid line. And again, less than or equal to means this would be to the left. So we know that going to the left from there is what needs to happen to be optimizing in our model. On the green side here, we've got that y has to be less than or equal to x minus 3. So again, x minus 3, you have an intercept of negative 3. This is 1x, that means the slope is 1. So rise 1, run 1, rise 1, run 1, rise 1, run 1, and so forth. You want to make sure you get all the way to that blue line so that we get where that intersection occurs. And I'm going to go all the way to the bottom because I never know where this last line is going to be. And now I've got that line, and its y is less than or equal to. So if you recall from graphing inequalities, that means below. So what we have so far is we need to be to the left of this blue line and below this green line. Okay, so we've got that whole bottom space so far. But now we've got this red line still. Y is greater than negative 5. So again, y now. So now we're going down 5 because this is the y-axis here. Oh, lost my Apple Pencil there. So the y, since this is the y-axis here, we're going down to negative 5. It's now just greater than, so this has to be a dash line. Okay, so that dash line is going across at y equals negative 5, but we need it to be greater than, so we're going to go up from there. So you can see now we need to be to the left of the blue line, below the green line, but above the red line. When you put all that together, that means this space right here is our optimized area, okay? And our optimized area, again, then we would just shade that area. And again, there's not enough context for us right now to know what that actually means in that optimized area. But we do know that this is the space that this company or team or group or whatever would want to work in order to look at what would be the best option for them. And again, it could be a route, it could be for profits, or whatever it may be. But that would be then the result of this linear program. And then we'd work off of that region, that little triangle there. And it's not surprising that it's a triangle because we had 3 lines. We'll look at one more here, and this one actually has 4 lines. So this would be a quadrilateral that we're looking at, most likely. And so we look at x is less than or equal to 2. Okay, so again, it's less than or equal to, and it's an x, so it's on the x-axis. So we're going to go to 2 on the x-axis here. Go all the way up, make it a solid line because less than or equal to, and it's less than, so this would be to the left, okay? So that's 1. Purple, I'm going to replace the purple. I'll use yellow on my iPad here. So I need it to be greater than negative 6 for this one. Okay, so greater than negative 6, again, this is x. So I'm going to go to negative 6 for x, and it's just greater than, so it's going to be a dash line because it's not greater than or equal to. Okay, so I have my line x is negative 6, and it needs to be greater than that, so it's going to be going in this direction. So we basically have our right and left bounds now. Dash line to the left, solid line to the right, and we're going to go in between those. Okay, now this green one you can see is going to take a little more work because this right now is not solved for y. So we're going to solve this for y first, and then we'll graph it. So I'm going to get my green pen here, and I'm going to take negative 3x plus 2y is greater than 2. I'm going to move my x to the other side. So right now it's a negative 3x, so I'm going to add 3x, and what's done onto one side must be done onto the other. So that gives me on my left side just 2y is greater than, and again, I'm going to write it in the mx plus b form here. So is greater than 3x plus 2. And now I need to undo the 2 that's with the y. So to undo that multiplication, I'm going to divide. So I've got now y is greater than, again, my slope would be 3 halves, so 3 over 2, and then x. My intercept is 2 over 2, so that's just 1. Uh-oh, my pencil lost again. And so that 2 over 2 means my y-intercept here is plus 1. So I'm going to go up here to y-intercept of 1, and my slope is 3 over 2, so I'm going to rise 3 and run 2, rise 3 and run 2. I'm going to go down 3 and back 2, down 3 and back 2, down 3 and back 2. I want to make sure that I cross both the yellow and the blue lines, and so that's why I connected all the way up past the blue and all the way down past the yellow on the left side. And again, this is just greater than, so this is another dash line here. Okay, so I'm going to connect these green dots here with a dashed line. So I'm going to dash, oh, I still don't have, keep losing my pencil connection here. So I'm going to put a dashed line here along the green line. Let's see if I can get my pencil back here. And that's a greater than, so the arrow would be going up on this one. So I'm going to put this dashed line in. And again, it's y is greater than that. So the y would be, this would be going up. So you can see now I've got between the yellow and the blue and above the green is what I'm looking at right now. Then we have one more here, which is y is greater than 2. And again, the y-axis is here. So this actually, I said this might be a quadrilateral. This will actually be, it is, but it's a little different than I was even thinking when I said that. So there's our y is 2. Again, it's dashed because it's just greater than. And greater than means going up. Okay, so the green, I just forgot that we didn't have an upper bound here. So we have lower bounds with the green and the red. But you can see, because it cuts this corner right here in the bottom right, that it is still going to be 4 sides. Okay, we've got right here, along the red, up the green, and up the blue. And so all of this area now ends up being our optimized region. Okay, and again, there is no upper bound, so this technically goes up forever since there's no upper bound. Now, again, a company might not be able to go all the way up forever because it might be a limited, eventually you run out of inventory or something like that, which would be then a top bound that we would add in at some point when they realize that. For instance, if it's using natural resources and they just don't know exactly where the ceiling is for that, they might not put that in there yet. But now this region, which used the yellow line on the left side, the blue line on the right side, the red line on the bottom that was dashed again, and then the green in the bottom right that just cut that corner where the red and the blue met, that allows us to see that optimized region here. So it followed all 4 rules. And again, that whole black area, anywhere in there would be considered optimized. And so the company would look at that space and look at trying to make sure that they set up a route that was optimized in that way, or manufacturing or whatever it may have been in that context. Thanks for watching. Thanks for listening. As always, if you have questions, please ask.